What if I told you one of the most promising solar materials of the last half-century started as a failure so obvious it looked like the end of the idea? In 2009, a new kind of solar cell produced exciting results, then quickly degraded because the material couldn't survive the environment it was placed in. It wasn't bad science. It was a brutal lesson. The physics was right, but the material system wasn't ready. Most research stories end there. This one didn't, because buried inside that short-lived device was a signal silicon couldn't ignore. A semiconductor that absorbed light incredibly well, could be tuned by chemistry, and could be processed at low temperatures, more like coating than casting. Today, that material family, halide perovskites, sits at the center of the fastest efficiency rise solar research has ever seen. Not because it's magic, and not because it's guaranteed to replace silicon, but because it changes what's possible when you treat solar as a materials problem instead of a manufacturing tradition. The real story isn't a miracle crystal. It's a new design philosophy, high performance from a material that's forgiving to manufacture, if you engineer the environment around it. So how did a fragile lab result turn into a global race? And what's still standing between perovskites and the real world? To answer that, we have to go back to the experiment that almost convinced everyone this technology was non-viable. We're trying to electrify a world that's growing more power-hungry every year. AI, data centers, heat pumps, EVs, industrial decarbonization. Demand isn't uniform everywhere, but the trend is clear. Electricity becomes a backbone of everything. Solar should be the obvious scaling solution, because the resource is vast. The bottleneck has never been sunlight. Its cost, speed of deployment, and how efficiently we can turn photons into usable electricity across real surfaces, not just perfect lab setups. Silicon solar has been an engineering triumph, but it also comes with realities. Energy and capital-intensive manufacturing rigid form factors and a maturity gap that makes it hard for new tech to compete without proving long lifetimes and bankability. Perovskites matter because they could attack multiple bottlenecks at once. Low-temperature processing, lightweight, and flexible formats, and the possibility of higher efficiency through tandems. Stacking materials so less sunlight is wasted. But this isn't solar solves everything tomorrow. Grid upgrades, storage, permitting, and supply chains still matter. Perovskites don't remove every constraint. They may remove one of the biggest, the cost and versatility of capturing sunlight at scale. In the mid-2000s at Toin University of Yokohama, Professor Tsutomu Miyasaka was working on dye-sensitized solar cells, an older approach where light absorption relied on dye molecules and liquid electrolytes. Progress was real, but incremental. Then his group tried something that didn't fit the usual plan, using a halide perovskite as a light absorber. Perovskites weren't new as a concept. Perovskite describes a crystal structure known since the 1800s. But perovskites weren't viewed as mainstream photovoltaic contenders, and the result was startling. Strong photovoltaic behavior, enough to suggest this material class had serious potential. Then the weakness hit immediately. The liquid environment degraded the perovskite. The device didn't fail slowly. It failed clearly. That should have ended the story. Instead, Miyasaka published a result in 2009 anyway, performance plus failure mode, side by side. And that's what makes this an accidental discovery story in the honest sense. The breakthrough wasn't a finished technology. It was a signal hidden inside a failure, showing material that could perform if someone removed what was destroying it. Halide perovskites are often described with the structure ABX3, a flexible crystal framework where different ions can be swapped to tune properties. That tunability is a big deal because solar materials live and die by their bandgap, which wavelengths of light they absorb. Silicon's bandgap is fixed. You can engineer around it, but you can't easily rewrite it. Perovskites, by contrast, can be chemically tuned across a useful range. Change halides, change cations, adjust composition, and you can shift what part of the solar spectrum they capture. But the bigger surprise is performance versus manufacturing demands. Many high-performing semiconductors require extremely strict purity and expensive processes. Perovskites often deliver strong performance, even when processed in comparatively simple ways. Thin films deposit from solution or vapor at much lower temperatures than silicon. This doesn't mean defects don't matter. They do. But perovskites have shown unusually strong performance despite imperfections that would cripple many other cheap semiconductors. That combination, tunable absorption plus relatively accessible processing, explains why the field accelerated so fast. And it also explains the next question. If they're so promising, why aren't they already everywhere? Because the same chemistry that makes them easy to process also makes them vulnerable. The early perovskite story had a brutal headline: amazing lab performance and terrible durability. Moisture, oxygen, heat, and light stress could degrade early formulations. In a lab, you can protect a tiny sample. In the real world, you need decades of stability through temperature cycles, humidity, UV exposure, and mechanical stress. So for years, a large part of the energy community treated perovskites as spectacular science, questionable engineering. And that skepticism wasn't irrational. Solar is infrastructure. Infrastructure must last. But something kept happening that made it impossible to dismiss the field. Performance kept improving, and the stability story slowly shifted from hopeless to engineering problem. That's the key pivot. Perovskites didn't need to become a perfect material. They needed to become a protected material system, where interfaces, additives, and encapsulation were designed as seriously as the absorber itself. Once researchers accepted that, the path forward became clearer. The rescue of perovskites wasn't a single miracle fix. It was a stack of engineering moves. Passivation, adding molecules or treatments that reduce defect-driven degradation pathways. Stabilizing interfaces where failure begins. Encapsulation, sealing the device so moisture and oxygen can't reach the active layers. This is not unique to perovskites. Many modern devices survive because of packaging, not because the core material is invincible. Composition upgrades. Early perovskites used less stable compositions. Later work moved toward mixed cation and mixed halide strategies that improved thermal and operational stability. But the most important structural strategy was this: tandems. Instead of fighting silicon, researchers started stacking perovskites on top of silicon. Each layer captures a different slice of sunlight that reduces wasted photons and pushes efficiency beyond what silicon alone can realistically reach. And it changes the commercialization logic. You don't need to replace silicon's entire supply chain. You can augment it. That's a much easier industrial path. And it's why perovskites stopped being a lab curiosity and became a platform. Perovskites didn't become a global race because one paper existed. They became a race because multiple labs proved the core idea could survive outside the original setup. Researchers like Henry Snaith helped drive the field forward by replacing the liquid electrolyte approach with solid-state architectures that dramatically improved viability. Others, including Namgyu Park, validated key progress and expanded the global momentum. What made this era unusual wasn't just speed. It was how openly the community iterated. Methods improved fast. Failures were documented. And the global research ecosystem moved like a relay race. And then the inevitable shift happened. Companies formed, pilots scaled, and the question became industrial. Can you make this with yield? Can you warranty it? Can you finance it? That's where solar technology stops being a science competition and becomes an infrastructure test. And that's the real threshold perovskites are now approaching. Perovskites are most likely to change the world first in the places where their advantages are clearest. 1. Tandem panels on rooftops and solar farms. Stacking perovskites on silicon can squeeze more electricity from the same area. That's not a niche benefit. It's a direct economic advantage in space-limited installations. 2. Lightweight and flexible solar. Because perovskites can be deposited in thin layers, they can enable power generation on surfaces that can't carry heavy glass and silicon modules, subject to durability and encapsulation. 3. Building integrated photovoltaics. Perovskites can be tuned in color and transparency, which opens the door to windows, facades, and architectural surfaces. Again, if stability and lifecycle requirements are met. 4. Faster, potentially lower capex manufacturing routes. Some manufacturing visions look closer to coating/printing than to wafer processing. That doesn't automatically mean cheap overnight, but it could change how quickly capacity is built if reliability and yield mature. This is not guaranteed dominance. It's a realistic path where perovskites win by doing what silicon struggles to do, expanding form factors and boosting efficiency without rebuilding the world from scratch. Two concerns dominate any serious perovskite discussion: durability and bankability. Silicon has decades of field data. Utilities and financiers expect 25 to 30 years. Perovskites must prove comparable reliability, not just in accelerated tests, but in real deployments. Lead. Many top-performing perovskites contain lead. The absolute quantity per panel may be small, but at global scale, this becomes a governance and life cycle issue: manufacturing, breakage scenarios, recycling, and regulation. There are nuanced answers. Strong encapsulation reduces risk, recycling can recover materials, and researchers are exploring lead-reduced or lead-free alternatives. But the constraint is real, and there's also the competitive reality. Silicon isn't standing still. It keeps improving, and its manufacturing ecosystem is unmatched. So perovskites face a clear challenge: prove lifetime, prove safe life cycle, prove manufacturability. If they do, they don't just become another panel. They become a new layer in the world's energy stack. Here's what makes the perovskite story credible. The problems are known and the solutions are being engineered systematically. For stability, the playbook is better compositions, better interfaces, better encapsulation, and real-world testing moving from labs into deployments. For lead risk, researchers are working on containment strategies, designing device stacks so that if damage occurs, the material is less likely to migrate, plus building recycling pathways so end-of-life isn't an afterthought. And tandems remain the most pragmatic bridge to mass adoption. Perovskites don't have to overthrow silicon. They can ride on top of it. That's why perovskites have moved into pilot production and early commercialization efforts, because the technology now has a believable migration path from lab record to industrial product. Not a miracle, a roadmap. And once a technology has a roadmap, scaling becomes an engineering race. 5 years from now, the most visible impact will likely be tandem products and early deployments, markets where efficiency per area matters and where reliability data can accumulate fast. 10 years from now, if durability and manufacturing yield mature, perovskites could expand into more form factors, especially building integrated surfaces and lightweight applications, while silicon remains the backbone. 20 years from now, if perovskites reach true infrastructure-grade reliability, the world could look different. Not because perovskites are magic, but because cheap, high-efficiency solar changes what's economically reasonable. Desalination becomes easier to justify. Industrial electrification becomes faster. Carbon management becomes less energy-limited. But the real limiting factors will still include grids, storage politics, and supply chains. Perovskites don't solve everything. They can make one of the hardest bottlenecks, capturing sunlight cheaply and efficiently, much less brutal. And that alone can reshape the pace of global electrification. Perovskites are part of a bigger pattern: solution processed, tunable semiconductors. The same mindset shows up in LEDs and display material sensors, thin film electronics, and manufacturing approaches that trade extreme purity for smarter architectures and forgiving materials. The deeper lesson is not perovskites are perfect. It's that the next industrial wave may come from materials that perform well without demanding perfect manufacturing conditions, because scalability is its own kind of power. This story is about timing. Perovskites are crossing from papers and records into products and warranties. That transition is where technologies either die or become infrastructure. If you're a student, this is a living example of how materials go from discovery to deployment. If you're an engineer, it's a case study in turning a fragile material into a robust system. If you're simply curious, it's proof that breakthroughs often start as failures that someone refuses to discard. The world doesn't change when a material is discovered. It changes when a material becomes manufacturable, reliable, and boring. Perovskites are approaching that threshold. In 2009, a perovskite solar cell worked, and then degraded so quickly it looked like the idea was dead. But that failure contained a message. The physics was worth saving. The last decade proved something important about the future of energy. The constraints we argue about, cost, efficiency, scalability, are often not fixed laws of nature. Their properties are materials and manufacturing, and those can change. Perovskites won't replace the sun or solve the grid overnight, but they might do something just as transformative. Make high-efficiency solar cheap enough, versatile enough, and scalable enough that we stop treating abundant energy as a rare privilege. That's why Future Forge Explored exists, because the future doesn't arrive as a headline. It arrives as a materials shift. And somewhere right now, in a lab, another failed material is doing something strange, just long enough to hint at what comes next. If you want to catch those moments early, you know where to be.